Video 7, Part 2. Part 1 was interrupted by a phone call from my son, who's at science camp. I apologize. The end of the last video showed the derivation of what is known as the Nernst equation. Remember again, this was the delta G, which was not at standard state conditions, that we calculated to judge spontaneity. Well, how do we judge the cell potential if we're not at standard state conditions? However, as we went through this derivation, this Nernst equation, how we developed this relationship of E naught minus 0.0591 divided by N log of Q, was we took into account R and T being at 25 Celsius. This equation shows the relationship of cell potential and the concentration of your cell components. So if we can go through an example of this together. So this first example problem gives us this balanced reaction with the E naught value. So that is where these would be at 1 molar concentrations. So this is the first example that we looked at right at the beginning of video 7, part 1. Well, what if the manganese concentration was 0.5 and the aluminum concentration was 1.50 molar? Okay, we know we're going to have to calculate E. We already have E naught. Well, this is what will allow us to calculate Q, of course, where our Q will be the concentration of your aluminum ion squared. Remember the law of mass action. Manganese does not show up in our Q expression because it is in the solid state, divided by the manganese plus 2 cubed. Aluminum does not show because it's in the solid state. So we have our Q. Oh, we need N. Oh, so we're going to have to look and take apart this equation a bit. Now, our aluminum is going through the oxidation. But as you see, our balance reaction is already showing 2 and 2. Oh, so to balance a 0 charge and a plus 6, we must need 6 electrons. So let's check to make sure that with our 3 manganese to create 3 manganese solid, that required the addition of 6 electrons, and yes it did. Yes it did. So we know that N is 6. So E will be E naught minus 0.0591 divided by N log of Q. So it will be the 0.48 joule per coulomb, probably full, but let's just see, minus 0.0591 divided by 6 moles of electrons, log of the aluminum concentration, 1.50 molar squared divided by 0.50 molar cubed, and this gives us 0.48 minus 0.012. Now, taking a log of we're getting an exponential, a base of 10, and so on. So do we need to say joule per coulomb? Well, we know our E needs to be in the unit of volt. And so this will be 0.47 volts. And didn't we say that if we had a higher concentration of the aluminum ion, a lower concentration of manganese, that would cause us to not have as great of a push, and the E would be lower than the E naught. Not by very much, but it still is 100th lower. The second example that I have on the second page for you, here you're just asked to do a little bit more work because you're given the 2 half reduction reactions. So it's up to you to first decide to get your balanced reaction which one you need to flip, and you're going to need to flip this guy. So when you flip him, and then to get all of your electrons to be equal, this is the situation that we'll get. If you'd like to pause it and then take a look at my work, but again, I flipped this second reaction. Remember, when you flip the reaction, you change the sign on your E naught. We need to multiply through the top equation by 2 to make sure that the number of electrons are the same, but now our N value is going to be 2 moles. But remember, when we multiply through, we do not change our value of E naught. We then get this as our balanced equation, and then your E naught of your cell is this. Well, as you see, we are not working with 1 molar solution. So when it says describe the cell based upon this given information, well, we need our balanced reaction. We need what the E would be, but we go from the E naught. So we would apply the Nernst equation, and we have our Q would be the concentration of VO plus 2 squared. Water does not show up in the overall equation for this. The zinc ion to the first power, VO2 squared, plus the hydrogen ion to the fourth power. Then, taking your E naught that you found and plugging in, we end up getting that concentration for the cell. Now, we could be asked, of course, to go ahead and structure this, to draw this, to do the line notation, but this lesson is definitely focused on the Nernst equation. And so again, please pause it if you need to look further at my work, and please, you, of course, try it yourself. I'd like to move on to the third example, taking our time to really process our way through that. All right. For the oxidation-reduction reaction of this, the appropriate half reactions are these. Balance the reaction, calculate the E naught, and K. Okay, so let's do these in the order that we're asked for it. So, we are given both reductions. We need to flip this. This will become our oxidation. So, we have the S4O6 - 2 plus 2 electrons yielding 2 S2O3 - 2. We've done nothing so far, so we are going to keep that at 0.17 volt. The second we are flipping, chromium plus 2 becomes chromium plus 3 plus 1 electron. Then the E naught is positive 0.50 volts. The only thing that we need to do is to make sure our electrons are equal, so we need to multiply this through by 2. However, the E naught will not be changed, so we can go ahead and get the E of our cell, which will be 0.67 volts here. Our balanced equation then is S4O6 - 2 plus 2 Cr plus 2 yields 2 S2O3 - 2 plus 2 Cr plus 3. I always like to give a double check to make sure we are completely balanced. For sulfur, 6 oxygen, 6 oxygen, 2 chromium, 2 chromium. I have a -2 plus 4 plus 2, -4 and plus 6 plus 2. Everything is balanced, so I have my balanced equation. Oh, I've calculated E naught. But then it's asking me for K. I'm asked for K. Well, the Nernst equation says that E is my E naught minus 0.0591 divided by N log of Q. Well, notice I'm not told anything about my concentrations. Oh, so I need to trust that we're at 1 molar. We're at 1 molar, especially because it's asking me for K, so I must be at equilibrium. And remember when we were at equilibrium, if we looked at this equation, yes, oh, please forgive me. Remember that we would say RT ln of 2, that this would be 0. We're going to do the same thing. So, 0. So therefore, E naught equals 0.0591 divided by n. Let me clean up my eraser marks. Very sorry. Log of K. So, let's plug in what we know. Well, we know it's 0.67 volts times our n, which here is 2 moles of electrons, divided by 0.0591, and that will equal log of K. Whenever I do the math and take the inverse log, I should get, and if I'm not mistaken, I need to take away 1 sig fig, so we should be getting 5 times 10 to the 22nd whole. So we can clearly see that if this is at equilibrium, then we are grandly favoring right, which is really good because then the reaction is pushing right, which is what we wanted to do. So that is the extent of what we are going to look at using the Nernst equation.